is Generalized Linear Models with examples in R, Chapter 4, and we're on question 4.9. Now, 4.9 is following off of question 4.8, where we looked at the Poisson probability distribution. So we're going to continue off of that. All right. So in that video, we found, the log likelihood, the score function, etc., etc., etc. And throughout all of that, we were using one parameter mu. And now we're going to reparameterize such that the log of mu is our linear model. Okay, and so we've already seen examples of this, I think in 4.6 and 7, where we further broke down the mu parameter into some kind of linear model. Okay, so you should check those out if that's a little bit unfamiliar to you. Okay, so with this new parameterization of our probability distribution, first we're going to find the score functions for beta naught and beta 1. So I adapted some steps from the book called Generalized Estimating Equations. And again, we went through those steps in some previous videos, so we'll kind of cruise through them right here, but roughly, in order to kind of accomplish this reparameterization, we choose our probability distribution, which we already have. It's the Poisson distribution. We write the joint probability distribution for the entire data set, which just means taking the product of that probability distribution over each observation. We then take we convert it to a likelihood, which just means, changing the order in which, the parameters in the data depend on one another. So it's just a restatement. Okay. And now we allow each observation to have its own unique parameter, or parameters in some cases. So we just take the mu, and we allow every observation, I, to have its own parameter. Okay. And now we can express this as the log likelihood. Okay. So we take the log of all of that. Okay. And you can follow the steps for yourself, but we come out here. And now we need to parameterize our log likelihood here to keep it within the desired confines of the problem. And so we have a Poisson distribution which is never negative. Okay, and so one thing that we could do is we could take the log of mu, right? That would make sure that it never goes below 0. Okay, and so that function that we're applying to the parameter, or parameters in this case mu I, is called the link function. So we're using the log link function, okay, which is what the question, where are we at here? Which is what the question is asking us to do. Okay. And then with that, we parameterize the model, right? So the log of mu is our linear model here, right? And so now we have reparameterized mu in terms of beta naught and beta 1. Okay. We could equivalently say, so we have that the log of mu is equal to, our linear model, but we could also take the exponent of both sides, or exponentiate both sides, I should say, and then we get mu is e to the linear model here. Okay. And so now we make these replacements for the log likelihood. Okay, so for this expression right here, okay, so everywhere where you see a mu, we put e to the linear model. Okay, here, right, and then everywhere where we see a log of mu, we put just the linear model. Okay, and so that becomes our log likelihood for this reparameterized model. Okay, so that wasn't actually part of the question, but we need to do that in order to push forward here. Okay. So remember that the score functions are just the first derivative of the log likelihood, okay, with respect to the parameter of interest. So now we have, so to get the score function for beta naught, we just take the partial derivative of our log likelihood here with respect to beta naught. Okay. And so again, I'll let you, work through the steps that are laid out here. But we ultimately come out with this expression for the score function with respect to beta naught. And then similarly for beta 1, right? So now we're taking the partial derivative with respect to beta 1. Okay. And we come out with this expression right here. Okay. So now we will, for part 2, we're supposed to find the observed and expected information matrices. And remember that this just means, so the observed information matrix is the negative second derivative of the log likelihood, or stated differently, it is the negative first partial derivative of the score function. Okay, and so we need to do this for beta 0, beta naught, for beta 1, as well as the cross terms so that we get the full matrix right here. Okay, the cross terms would be this and this. Okay. So we can. So again, I'll let you walk yourself through these steps here, but ultimately we come out with this expression for the observed information matrix with respect to beta naught, and then we're just calling this mu. So I'm just going to use that just to simplify the notation. And then if we want the expected information, well then I just need to take the expectation of that guy right there. Well, so the expectation of the observed information matrix, well, in this case, the expectation of the parameter mu is treated as a constant, and so the observed information is identical to the expected information, in this case. Okay, so now similarly for the observed information with respect to beta 1, so this is the negative partial second derivative of the log likelihood with respect to beta 1, okay, or the negative first partial derivative of the score function with respect to beta 1. Okay, so you can push through all of that, and you ultimately get an expression like, well, you get this expression. Okay, and again, simplifying our notation, e to the linear model, we're just calling mu, so we get this expression. And now if we take the expectation of all of this, it is identical to itself. Okay, so we're taking expectation with respect to y. So we get the observed and expected information matrices are the same for beta 1. And now for the cross terms, so this again is a second derivative of the log likelihood, but we take the first partial derivative with respect to one of the parameters, and then the other derivative with respect to the other parameter. Okay, and you can reverse these, and it's just fine. It doesn't matter. It doesn't matter in these cases typically. And so we could restate that by saying, okay, well, we're going to take the negative partial first derivative with respect to beta naught of the score function for beta 1, and that is also going to equal, again, in this case, in these cases typically, the negative first derivative, partial derivative with respect to beta 1 of the score function for beta naught. So, if you just look at that, I'm sure that you see the pattern. And so I'm just solving both of these simultaneously, but eventually they become the same thing, okay? And so they just become, this guy. So we have a negative and a negative, so those cancel out, so we get this. And again, just simplifying the notation, e to the linear model just is mu, we're calling that mu. And once again, if we take the expectation of that, it is the same as the expected, the observed information is the same as the expected information. So we can wrap all of that up into this nice matrix right here, okay? Where again, for every entry, the observed and expected information is the same. Okay, So now finally, for part 3, oh, I forgot to paste the question in there. Let me paste that question there. Okay, so we want to find the standard errors for our coefficients. Okay, so for that, we need to find the variances, and the variances are given by the inverse of the expected information matrix, right? So we need the inverse of this guy right here. And so in order to do that, for a 2 by 2 matrix here, we do a couple of things. So one, we need to get this scalar term out here, and this is just the determinant of this matrix, and the determinant of a 2 by 2 matrix is these diagonal terms multiplied by each other minus these off diagonal terms multiplied by each other. Okay, so 1 over that. And then we flip this, we flip along the main diagonal, and then put a negative on the off diagonal terms. Okay, so this becomes our variance matrix. So there's probably some simplifications that we could use here, but let's just push through. So the standard error is going to be the square root of the variance for the coefficient that we're interested in. So the standard error for beta naught is the square root of the variance for beta naught. Okay, well, so the variance for beta naught is this term divided by this scalar term, right? Because the scalar term pushes all the way through. And we get this. Again, we could probably simplify this, but this is, I think, good enough. And then similarly for beta 1, oh, you know what, there's an error right there. Let's fix that. That should be for beta 1. Okay, so now we find the variance term for beta 1, which is this diagonal term divided by, again, the scalar, which just gets pushed all the way through. And it's the square root of that. That's the variance for beta 1. Okay, we will call that good.